Magnetic fields also cause a force on charged particles, as electric fields did, although the way that works out is fairly different. The magnitude of a magnetic force, the magnetic field is represented by the variable b. It is a vector, it has a magnitude and a direction, but just the magnitude of the magnetic force is given by q, b, b, sine theta. Q is the charge, v is the speed of that charge, b is the magnitude of the magnetic field, and the theta is the angle between the velocity and the magnetic field. So if v and b are in the same direction, or they're, if they're parallel or anti-parallel, they're pointing in opposite directions, then we've got a sine of 0 or a sine of 180. So there is 0 magnetic force on a charged particle that is moving in the direction of the magnetic field. Then the force is maximum when the velocity and the magnetic field are perpendicular, because then they're taking the sine of 90, which is 1. Now this force is actually a cross product, and we'll talk more about what that means in a minute. But this relationship between the force and the charge and the velocity is actually kind of what defines the magnetic field. The magnetic field is, just rearranging this equation, it's just the force over the charge times the velocity times the sine of theta. The unit for that is the Tesla, named after Nikolai Tesla, who was kind of a scientific visionary. He had a lot of ideas, and people thought he was kind of crazy, but then nowadays they're finding out that more and more of the things he said are actually correct and useful. Yeah, he's an interesting fellow. Tesla is represented as a capital T, and if we just follow dimensional analysis from this guy right here, well, maybe not directly, but it's equivalent to a Newton per amp meter. So the meter comes in the velocity would be meters per second, and the charge would be, a coulomb. So we'd have a coulomb per second. That becomes the amp. So a Tesla is a Newton per amp meter. The Tesla is actually really big relative to magnetic fields that you generally see. So there's another common unit called the Gauss. Uni's phone went off and she ran from the room screaming. No, not screaming. She just ran away. The Gauss is a unit that's commonly used, and 1 Gauss is just 10 to the minus 4th Tesla. And that's just used because it's more convenient for the magnitudes of what magnetic fields actually are. Now, this force, this QVB sine theta, if we look at the vector stuff, it's actually Q times the velocity crossed with the magnetic field. The cross product is where that sine theta comes out. And I think you guys have probably done cross products in calculus, but we don't need to know how to do that because we have the QEV sine theta, but we need to know how to determine the direction of the force based on the cross product. And we do that using the right-hand rule, which we talked about when we were doing rotational stuff, torques and whatnot. So the velocity will have some direction, the B field will have some direction, and we can figure out the direction of the force based on that. Just a couple of notes. If you see a symbol like this is generally used to indicate that the B field is coming out of the page, i.e. pointing upward toward you. So, it's pointing in this direction. You can see the end of my my pen there looks kind of like that circle with a dot in the middle of it. And I guess that's kind of a 3D envisionment of an arrow going toward you. Anyway, and you go the other direction. I don't know how that works. It's a circle with an X through it. I guess that's an arrow going away from you somehow. But that means that something is going into the page. Okay. So we determine cross product using a right-hand rule. So let's say, for example, we have a velocity going to the right, a particle, with a velocity that's going to the right, and then the B field is pointing up. Then, to determine the direction of the force, we follow the right-hand rule. So to follow the right-hand rule, you point your hand in the direction of the first value, in this case the velocity. You're taking the velocity cross with the B field. So you point your hand in the direction of the velocity, curl your fingers toward the B field, and the direction your thumb points is the direction of the force. So in this case, the force is out of the page, because that was the direction that my thumb pointed, out of the page. Another way of thinking about it is you can use your first three fingers, your thumb and your pointer and your middle finger. Stick your pointer in the direction of the first vector, then you point your middle finger in the direction of the second vector, and then the direction your thumb points is the direction of the resultant when you take your cross product. Let's say we had a velocity going down and a B field coming out of the page. In that case, you have to contort your body a little bit, but you have to point your fingers in the direction of the B field and the direction of the velocity, which is downward, and then you have to curl your fingers in the direction of the B field, which is out of the page. And as you do that, your thumb points to the left. So in this case, the force is in the leftward direction. They don't have to be perpendicular for this to work. If I have, say I have a velocity going up and a B field, pointing this way, you still do the same sort of thing. My velocity is up, and my B field is up and to the left. I still curl my fingers this way, and we get a force that is going out of the page again. So that is how you use the right-hand rule. I could also kind of go the other direction. I could say we've got a force going to the right when we have a velocity going, say we have a velocity going downward and a force to the right. Well, that means that my hand needs to go downward while my thumb points to the right.
Attention.
So
All students and parents will need to.
So that means that if I put my fingers in the downward direction of the velocity, and I curl my fingers in some direction, my thumb ought to point to the right. So I have to kind of contort myself around here. I want to point down, and I want my thumb to be to the right. My hand needs to go this way, and then my thumb points this way, and my fingers would curl kind of in the downward direction. So we don't necessarily know the B field is straight down, but we know it's somewhere, down and maybe toward the bottom of the page a little bit. But you can figure out the general direction of it. And if you're given a statement like the B field being perpendicular to if you say the B field is perpendicular to the velocity, then we could say unambiguously that it is going into the page.